Tuesday there was kind of a more lecture type orientation on greenhouse gases and feedstock production. Today is kind of going to be starting to get to know one of the tools that you're going to use, namely the DaySet model, which is a derivative of another model called the century model, and they're not too different in some ways. The DaySet model is the one that has end-tool flexibility. So I've got actually some slides that are, generally when we teach new people how to use the model, a lot of times we kind of go through the century part because it's a little bit, and then that's kind of gives you the main stuff you need, and then there's some kind of add-on stuff in the DaySet. So there's that. Mark Easter, who's a research associate that works with me, is going to be here. Is going to wander in about a half an hour. He's going to have some data sticks, and on that is going to be. Can we get internet down here? Wireless internet? Does it work? Okay. So go ahead and if you're not logged on, you can log on and get on the internet. When he comes, there'll be one program to download, and then you'll have a folder of stuff that you'll have a few data sticks, and you'll create under your C drive. Is there any chalk? There's definitely not chalk in there. And then he's also going to have a computer, okay? Because you need a laptop, right? Okay, so you'll be getting your laptop, so no worries. But it's coming with the delivery. So basically, under your C drive or something, you'll create a directory called DaySet, and everything on that stick you'll copy into that directory. And the system is set up that using this graphic user interface, it kind of makes it easier for a beginner to run this model. It kind of expects to find everything under that root directory, okay? So it's not under program files, it's just, C and then DaySet, the root directory. The other thing is there's a text editor that is specified for that system that's called Notepad++, which is a free download. And one of the things you'll have to do, but wait until Mark comes. If you've already got Notepad++ on your system, then you're good to go. If you don't, then it takes about 2 minutes to download. Okay, so I gave you a little bit of an orientation on kind of modeling soil organic matter and stuff on Tuesday. And so now is a little bit more of a practical with respect to kind of using this particular model. So I want to quickly go through a few slides that give, talk a little bit, to give you a little bit more of an idea of the kind of the structure of the model and some background information. But I'm going to kind of whiz through that. But I don't know. And I sent out the slides like at 2 o'clock or something. So I apologize for the lateness of that. But you can also use this and go back and if you just want to use this as kind of a little bit of a reference manual type material. Okay, so a little bit about this model. Okay, this model has been kind of in operation for about 20 years, developed here at CSU. Maybe I'll dim the lights here, make it a little bit easier to see that. Some of you are already working with it or have heard about it, something like that. Bill Parton has been the main developer of that. He gave one of the lectures in the 100 seminar series. It's a biogeochemical model, so it looks at carbon and nitrogen. There's a version of the model. You can also simulate phosphorus and sulfur in the ecosystem, but it's not used very much. It was developed a number of years ago with people who were working with phosphorus in particular, but it's kind of been a little bit dormant. One of the nice things about the model and what makes it particularly useful is you can do sort of any type of terrestrial ecosystem virtually, okay? And so that's good for this sort of thing, right? Because a lot of times you're dealing with land use change, okay? You got pasture and you convert it to cropland, or you got cropland and you convert it to switchgrass or something like that. So you can, seamlessly simulate all these different kind of systems. There's two kind of main plant modules that are a little bit different. There's kind of one that's for herbaceous vegetation, as you can imagine, annual crops and grassland, and then there's a forest submodel. If you're growing trees, then you have things like wood and stems and branches and stuff like that. So that's a little bit different. There is something called the savanna model. You're not going to be using that if you had trees and grasses growing together and stuff like that. And I already talked some about the solar organic matter, probably. But stop me if you. Okay, now this I'm talking about the century model. So there's a couple of distinctions. The day set model is more recent. It is called day set from daily century. It has a 1-day time step for the model integration. Okay, all of these models are essentially systems of differential equations. Okay, they're doing and this model is also a kind of a one-dimensional model in the sense that it looks at, say, theoretically a square meter of soil surface to to depth, and so that's kind of like, it's not a model that simulates a landscape, that it has connectivity between an upland and a lowland so that you get things like overland transport and flow. It's not one of those kind of models. So think of it as think of it in your mind as a square meter or as a field that is essentially assumed to be homogeneous within that spatial unit. Okay? The century model, this is, but it kind of holds. So what do you need to run the model? There are, in terms of just running the model, you need some weather data or climate data. Okay, basically max and min air temperature and precipitation. Now, the daily version, instead of monthly averages of these things, it uses daily weather. Okay, but century model uses monthly weather. You need some information, but this is kind of contained in some of the parameter files, but basically something about the litter, the type of plant litter you have. There's soil texture, atmospheric soil nitrogen inputs. Those are generally things that actually are also kind of supplied in the parameter files, and then something about the initialization. But we'll get more into that. This is in terms of the kind of the external, outside the model boundaries or initial conditions kinds of stuff. And the main thing, though, that you guys are going to have to deal with is going to be setting up the management inputs. Okay, what plants are you growing? How are you growing them? When are you harvesting? All this kind of stuff. You also need to define some of the soil properties. Okay, this says soil texture, and that's kind of a minimum, but there are some other soil properties that, and actually for this exercise, I think we've set it up so the only soil variable you'll deal with is soil texture. So in other words, sandy soils versus clay soils versus silt loam soils, something like that. I think we already talked about that the soil type, is going to affect water relations, it's going to affect organic matter storage, and therefore it's going to also affect things like N2O, plant productivity, etc. Okay, I'm going to go really quickly through this. I showed this, I think, on Tuesday. This is basically how the model looks in terms of the state variables, okay, the stuff that the model is simulating for the below ground part. So it has these three compartments of soil organic matter. This is kind of the secondary decomposed material. It also has fractions, fresh plant residues into two different pools. Most of this stuff you don't really have to know a whole lot about. Things in the model that affect decomposition rates are things like moisture and temperature and soil disturbance. If you till the soil, if you physically disturb it, that affects decomposition rates. As I mentioned, I think before too, the soil texture influences kind of the transfers between these different pools, so it has an effect on
ultimately on kind of the mean residence time of the soil organic matter. Active pool kind of represents soil microbes and microbial products with a very short turnover time on the order of months. A slow pool represents kind of secondary decomposition products that are partially stabilized by things like, they're partially stabilized by being associated with mineral surfaces and things like this, and so it has kind of decadal scale turnover. And then you have this passive pool, and this one isn't going to change very much over time, but it's actually important in terms of, what the, how the model behaves. I guess you'll probably see that a little bit later. I wouldn't be concerned about it too much, but it is, it is a part of the soil that represents the really kind of recalcitrant stuff that turns over very slowly. So that can be things that are, highly stabilized on mineral surfaces. It can be things like residue charcoal that microbes don't want to eat, and stuff like this. Okay, and so I mentioned before nitrogen, phosphorus, sulfur pools, but this just shows the nitrogen part. So you've got a carbon part, and then of course you've got organic nitrogen as a component of all these different compartments, right? So you've got this cycling of organic nitrogen, and then, a lot of you, I guess we haven't talked a whole lot. Well, I talked a little bit about mineralization, so the decomposition of that organic material by microbes, and then some of that nitrogen is eventually released in mineral forms, okay, as ammonium ions, and then that can be converted into nitrate ions, and that's the part of the mineral end cycle that is important for particularly nitrous oxide classes. Okay, so it's not all that informative a diagram, perhaps, but soil organic matter pools, I think, you can read this on your own. Again, it kind of has to do with some of the ways in which the model functions. We just point out it's got a simple water balance model. Okay, you can get very complicated water balance models that look at, preferential flow and flow during different kinds of pathways. This is what you kind of call a sort of a tipping bucket model, but it actually works fairly well. The idea is that you have different soil layers, okay, and the soil has pore space in it. And the amount of water, how water flows depends on kind of the configuration of that pore space. If you have lots of small pores, then, there's a certain, there's always a gravitational force on water, right? And so if water is in a big pore, it's going to drain out and eventually leave the soil. If water's in a small pore, it can actually be held against the force of gravity, and that's called, capillary water, essentially. And how does that water get out of the soil? Well, it generally gets sucked out by plant roots, okay? And so that's a, 2-minute, we haven't really discussed soil. I'll get into soil water a little bit next Tuesday to give you guys a little bit more of an idea, the people that aren't biologists here. But basically, so you've got drainage or, vertical flow, largely this kind of gravitational water. You've also got uptake via the plant through transpiration, okay, and that's going to be a function of, the plant characteristics. You also have bare soil evaporation from the surface. So the surface is subject to just normal evaporation, but normally, deeper soil layers, if you don't have a plant present, you can dry out the surface layer, but below that, it pretty much will stay moist, kind of almost indefinitely. So you got snow melting, all this kind of stuff, but that gives you an idea. So you are going to be simulating a dynamic water balance in this. And one of the things that we're going to do as part of your, your environmental metrics is you can get out, water balance terms